we're going to look at two types of limits of the function f of x, y. So two types of very specific problems that I might ask about. And one of those types is going to be given a particular limit. I'm going to tell you it does not exist. We're going to verify it. We're going to verify that the limit does not exist. And so I'm going to show you how that works. This is manageable so long as the algebra is not too messy, but it certainly covers a case. It's easier to do this than to prove it does exist, and hopefully that will become clear as we go along. So the example we're going to look at is if the x and y values approach the origin, or 0, 0, what happens to this expression, x plus y over x plus y squared? If you begin with direct substitution, this is going to be 0 divided by 0, which is called indeterminate, which means, again, we don't know if there is a limit or not. This means we're not done yet, is what it means. And the goal is to, if we're going to approach the origin 0, 0, we're going to approach from different directions and just see what that means in an algebra sense. What does it mean to approach from different directions? So what if we were to approach 0, 0 on the x-axis? What would that look like if we were approaching the x-axis? What if we were to approach the origin either from the right or from the left? What would that look like? First, I want to note that the x-axis is where the y values are equal to 0 already. The y values are already 0. So what that means is we're going to take our algebra expression, x plus y, but y is going to be 0, and x plus 0 squared. And now all we have to do is find out, well, what happens if x approaches 0? You see how that works? If y is already 0, now we have a single variable limit to look at. Well, it turns out that this expression reduces to 1. X divided by x is 1, and this comes out to be 1. So there's a value there. Now in 3 dimensions, what that means is x-axis, y-axis, z-axis. So x is approaching 0 and y is approaching 0. We're approaching this location on the xy plane. But see, the function, and let's see, it's called here, this is f of xy. That's another name for z. So what this one means is if you approach the origin from the x-axis, your z value is getting closer to 1. So the graph must be approaching that z value from this direction. Now, let's try approaching the origin from a different direction. Let's approach 0, 0 on the line y equals x. That would be in the two-dimensional world. Let's approach from this direction. Y equals x goes to the origin. On this 3D graph, we're going to approach from here. So that's a different direction. We're approaching the origin in the xy world on that line. And let's find out what happens to z. So if y becomes x, then my algebra for my statement becomes x plus x, because now y equals x. And that's over x plus x squared, because y is now equal to x. And x and y both approach 0, but now I only have to worry about x approaching 0 because I've replaced every y value with an x value. Single variable now. So I did this approaching from one path. Let's see what happens here. Let's see, this is the limit. X approaches 0, 2x, and the denominator, if I factor out an x, I'll have 1 plus x left over. Looks like I'm not quite done yet. I can reduce this. Limit x approaches 0, 2 over 1 plus x. Now if x is equal to 0, I get the number 2. These are different. That's different from this one. Visually, what that means is if I approach the origin from this direction, my z value is going to be 2. Well, remember, these must be the same. You can't approach from two different directions and get different answers. So therefore, the limit does not exist. Okay. Now, just for kicks, I'd like to show a different variation of this problem. Okay, different variation of this problem. So let's move this aside. Same problem. Okay. All right. Let's approach zero, 0, those x and y values right here. Let's approach it from the y-axis. Let's approach it vertically. On the y-axis, and on the y-axis, that's where you will find x's are 0 already, but y is not yet. So I'm going to change this problem. Wherever it says x, I'm going to plug in 0 plus y squared. And now I'm only interested in what happens as the y values are approaching 0 in this two-dimension picture here. And if I reduce the algebra, I'll get limit y approaches 0, 1 over y. This is undefined. That's undefined. That's an exclamation point. That's kind of a big deal. If there's an undefined value in any of our paths we're approaching, that is sufficient to show that the limit does not exist. So, since one path is undefined, and just so you know, I only found one path. There may be more than one path is undefined. One path is sufficient then the limit does not exist. That is sufficient by itself to demonstrate the limit does not exist. So if the directions ask you to show that the limit does not exist, you have two options. Find two paths with different limits and make sure to state they have to be the same. They're different. The limit does not exist. That's your conclusion. Or find one path that is undefined, and then that's enough to prove the limit does not exist. Now when I create examples for assessing students, I don't go over the top with how many paths can you choose, but this is one way to tackle a problem related to limits. Notice how much easier it is to do this. All you have to do is keep going until you find two that are different or one that is undefined. There are infinitely many paths to check though. Proving the limit does exist is much more difficult. So we will try another technique coming up. See you then.